The petroleum refinery sector is the second highest ranking sector for greenhouse gas emissions, emitting an average of 1.23 million metric tons of carbon dioxide, according to the Environmental Protection Agency. To make matters worse, the demand for liquid fuels such as gasoline is expected to increase about 20 million barrels per day by 2040. With environmental regulations becoming stricter, such as the Clean Air Act, a more environmentally sustainable process needs to be implemented. It is up to us to find a solution that balances the increasing demand and decreasing environmental impact while still remaining profitable. Traditionally, gasoline is made from refinery conversion processes such as cracking, isomerization, alkylation, and the most prominent, fractional distillation. Although they are efficient processes, they produce toxic BTX compounds, particulate matter, nitrous oxides, carbon monoxides, carbon dioxide, and sulfur dioxides. Luckily, a recent alternative process has arisen to improve petroleum refining at lower costs and emissions, and it's known as methaforming. This process, created by new gas technology synthesis, reduces the naphtha desulfurization, reforming, isomerization, and benzene removal of gasoline production into a one-step process that utilizes a catalytic bed reactor containing a silica zeolite catalyst. New gas technology synthesis reports that methaforming reduces capital costs to as little as one-third of traditional costs, reduces energy consumption by removing the need for hydrotreaters and reheat furnaces, and lowers emissions by reducing 0.5 tons of carbon dioxide per ton of naphtha used.
Our team was tasked with the challenge to design a methaforming unit to be implemented into an existing refinery in Texas City, Texas. This unit would produce 5,000 barrels per stream day of a gasoline blending stock with a research octane number of 90 through the conversion of full-range naphtha and ethanol. The process would also produce hydrogen-rich gas and liquefied petroleum gas as valuable byproducts.
When considering the objectives at hand, the research octane number and the production rate can be seen as the most important factors. The research octane number is a way to measure the quality of gasoline, which affects the combustibility of the fuel at low temperatures and pressures. A higher run will lead to a higher requirement of compression for combustion, which will lead to a more efficient engine and less of an environmental impact. A lower run will lead to the risk of knocking in the engine, which is premature combustion of the fuel in the engine causing damage.
The methaforming unit comprises the following process steps, and the entire unit was modeled on Aspen Plus. An ethanol and full-range naphtha feed stream are mixed and preheated before entering a catalytic bed reactor. Full-range naphtha is obtained from crude oil distillation and comprises of light hydrocarbons and heavy hydrocarbons. Full-range naphtha consists of N-paraffins, I-paraffins, olefins, naphthenes, and aromatics. As the exact composition of full-range naphtha varies based on the type of crude oil used, a pseudo-naphtha stream was synthesized using a beta distribution of a gas chromatography analysis of naphtha in previous literature. The preheating is performed using a cross-exchanger, where the hot reactor products are used to heat the reactor feed. Heat integration techniques were performed to optimize the cross-exchanger to ensure a 10-degree temperature difference between the two outlet streams.
Further heating is performed with a fired heater in which fuel gas and air combust to increase the reactor feed to the operating temperature. Within the reactor, the following reactions convert full-range naphtha to methaformate: dehydration of alcohol, aromatization of olefins, alkylation of aromatics, aromatization of paraffins, and isomerization of paraffins. The reactor was modeled using Aspen Plus and has an operating temperature and pressure of 400 degrees Celsius and 0.9 megapascals.
There were multiple attempts at simulating the kinetics of reactions in Aspen. An attempt was made with the R-plug block, and 22 reactions and their respective activation energies and rate of reactions were inputted. This block was not successful at modeling the reactor because Aspen Plus was incapable of running with the reactions due to the presence of naming errors that could not be eliminated. An attempt was then made with the R-Gibbs block, where the reactions and their stoichiometry were inputted. This attempt was also unsuccessful because the simulation could not reach equilibrium with the specified reaction due to them being linearly dependent. The R-Equal block was then used, and the reactions, their stoichiometry, and their temperature extents were inputted. The temperature extents of each individual reaction were then altered in order to achieve the desired compositions. The team was able to achieve the component compositions close to desired set points while maintaining appropriate mass balances around the reactor and with no errors throughout the entire simulation. However, it was soon deduced that the reactions are not at equilibrium and they are indeed kinetic due to the differences in their temperature extents. Some reactions are significantly faster than others, and meanwhile, some reactions are favored in the forward direction while others are favored in the backward direction. Despite this, however, the REQUEL was successful at modeling the reactor in Aspen Plus and was used for the simulation.
The reactor products are then cooled and sent to a high-pressure three-phase separator that operates at 90 degrees Celsius and 1.2 megapascals, where light hydrocarbons exit as hydrogen-rich gas. Effluent water is another output of this separator and is sent to the on-site wastewater treatment system.
The remaining liquid hydrocarbons are preheated using a cross-exchanger similar to the one around the reactor and sent to a distillation column. Within the distillation column, separation of liquid mixture occurs through differences in boiling points through a process of repeated vaporization and condensation. The light hydrocarbons of the feed, which are the distillate products, are vaporized and travel up the column. It is then sent to a partial condenser and reflux drum, where the vapor condenses and the liquid condensate is sent back through the column. The reflux drum further separates more hydrogen-rich gas and liquefied petroleum gas. The hydrogen-rich gas is combined with the HRG from the three-phase separator, creating a total of 1,600 barrels per stream day of HRG, which is then recycled and to be used throughout the refinery. The 1,600 barrels per stream day of liquefied petroleum gas is stored and sold. The heavy hydrocarbons of the feed are condensed and travel down the distillation column and sent to a kettle boiler, which it is partially vaporized and sent back to the column. The bottom of the column produces 5,000 barrels per stream day of the final methaformic product, which has a RON of 89.2. It is then cooled and sent off-site. The capital costs of all unit operations were calculated following the Product and Process Design Principles textbook. Additionally, because this system takes place in an existing refinery, the allocated costs, the cost of land, and the cost of royalties have been adjusted to zero. Using the factor of the integrated facility, the cost of the total capital investment is $13.1 million. Additionally, the cost of labor, maintenance, overhead, depreciation, along with the feedstocks of the full-range naphtha and ethanol, and the utilities of fuel gas, cooling water, steam, and electricity were all taken into account when calculating the total annual cost. The total annual cost of production is $150 million. The methaformant and the liquid propane gas will be sold for a total of $178 million annually. This results in a net profit of $50 million, an ROI of 110%, and a payback period of 230 days.
In conclusion, methaforming is an appropriate alternative to crude oil reforming. The process was able to produce a volumetric flow rate of 5,000 barrels per stream day of gasoline blend stock with a high research octane number, along with hydrogen-rich gas and liquefied petroleum gas as byproducts. Although the reactor was successfully modeled in Aspen Plus using REQUEL, it is evident that the reactions are not equilibrium reactions since they all require different temperature extents to achieve the desired compositions. Therefore, it is recommended that a kinetic model is performed and modeled to properly portray the dynamics of the methaforming reactions. Additionally, it is recommended to implement a second reactor that performs continuous catalytic regeneration to reduce annual costs and to increase the life of the catalyst. All in all, conversion of naphtha to methaformate is a profitable refinery process that minimizes environmental risk while reaching product demands.